How are you doing? Done or need another video? Pretty well done. Okay. So I don't know if a picture again is necessary, but it's right on 0 to 5. Okay. So this to me is the general idea. Sum of many rectangles. See? And what's the delta x? 5 over n. And at what points, at what x's do we calculate the heights? 5 over n, some number of times. In what cases do I have a something plus the delta x in there? When it starts somewhere besides 0. In that case, in this case, that was not an issue. Okay, so cool. I is the counter starting from 1 and going to n. Now what did you do? Plug in the function in the problem. In this case, the function says blank minus 1 squared. And then the blank goes 5n. All right. So now what? Okay, we really want to blow this up into lots of little sums, and how fast you do that is up to you. If I expand that square, then I would first have this squared, so I'd have 5 over n I all squared, and then I would get what? Negative 2 of those things? Yes. And then at the end it would end at 1. Alright, so now we're ready to blow it up into 3 summations. The first one will be when I distribute this and pull stuff out. So what do I get when I pull stuff out? 5 over n cubed. 5 over n cubed times the sum of a bunch of I squareds. If I then distribute 5 over n to that, what's out front? 5 over n squared. A negative 2 and a 5 over n and the sum of a squared and the sum of a bunch of i's. Okay? Oops, that's where I was pointing with that mark. Alright, and then the last is 5 over n times a bunch of 1s. Cool. Alright? Doing well, doing well. Now what?
Then
we use those formulas for the I stuff. Alright? So the sum of a bunch of squares, and again, you don't have to memorize these. I will give them to you. But the sum of squares is that formula. Alright? Assuming it ends at n, which in this case it does. Minus 2 over 5. 2 times 5 over n squared, and the sum of a bunch of plain old numbers. And what's the sum of a bunch of 1s? N. Okay. That I'm going to call A sub n for area as a function of how many rectangles. We? Alright. Now that would give me an estimate based on any number of rectangles, but what's the goal to get the perfect area? Infinite number of rectangles. So I need to take the number of rectangles, which is represented by n, to infinity on that function. Here's where I had several questions yesterday before, after school. I must have rushed through it. They didn't understand what I did actually. So I'm doing end behavior on this big thing. And if you want to rewrite it, cool. I don't feel like it's necessary. It's value added. If you want to clean it up, canceling ends and stuff, fine, go for it. But again, I don't feel like it's necessary. I first verify that the powers on the ends are correct. Do you agree? This is n cubed in the denominator, and this is overall n cubed in the numerator.
Yes.
So as n gets infinitely large, it'll be just the ratio of the coefficients of the n cubed, and all the other little stuff doesn't matter so much, yeah? So in the numerator, what are the coefficients? 5 cubed, or 125, and 2, and then the denominator? 6. All right. When I go to this guy, same deal. Power-wise, it's n squared in the denominator and n squared in the numerator. So there's a match And I could just look at the coefficients. What are the the coefficients in the numerator?
2 over 2 and 25.
2 and 5 squared are 25 and 2 in the denominator. And the last one, surely that just goes to
5.
5. All right. So that said, I'm getting something like 125 thirds minus 25 plus 5. We 125 thirds minus 20 if you like. And 125 thirds minus 60 thirds is
65.
65 thirds. If I'm so inclined, how can I check my work?
Integrate.
I can integrate the antiderivative from 0 to 5 of x minus 1 squared. That's a good review of integration technique. How would you integrate that? You could expand it, but then you would have to use sub it. That's fine too. Or I guess you could just not even use sub it. I'm just going to expand it. How's that sound? Okay. So I would get something like 1/3 x cubed minus x squared plus x from 0 to 5. That is 125 thirds minus 25 plus 5. That is exactly what we had there. So we did that. All right? Assuming we did everything below that, right? How'd it go?
Amazing.
Okay, cool. The next one starts, I gave you a cleaner function, but I started it somewhere besides 0, so hopefully. All right. So let's go to the notes real quick, just a little bit. I'm not going to go through this whole packet. Most of it's problems. And I totally mistitled this. Would you scratch out, after fundamental theorem, just scratch out, it's not inverse trig, and it's not something, whatever else I said.
Area by calculus.
Yeah, no by area, and no inverse trig, just fundamental theorem of calculus. Yay! Okay. So this is review, so I'm going to cut my amazing fundamental theorem lecture down to its nitty-gritty, but fundamental theorem of calculus, so cool. First of all, from the last couple of days, we know that a definite integral comes from the infinite rectangle idea. Okay, infinite rectangles to estimate area. And through the limit of many, this is so, just it blows my mind. We talked about this yesterday, but as you take more and more rectangles, where does the width go to?
dx.
It's dx. And what does dx get? It gets infinitely small. So the base of each rectangle goes to 0. So that feels like the area should be 0, right? But the number of rectangles goes to infinity. So that feels like it should be infinite. And yet, it's somewhere in between. There's the play between tiny rectangles or infinitely many rectangles, infinitely thin, and that is what the definite integral is doing. Okay. Now we know from calculus experience that when you evaluate a definite integral, what 2 steps do you do? You integrate or anti-differentiate, and then evaluate at the upper minus lower, right? Okay, so just again to review, I know Ms. Cannon talked about this, but why? Why do you integrate? What does an antiderivative have to do with it? Why do you anti-differentiate?
Find the area on.
Why do it? Why?
Find the area under the curve.
Okay, but why would area under the curve have to do with an antiderivative? Okay, physics actually, it serves pretty well. That's how Newton came up with it. All right, so let's talk about this. Why? That's what I want to just touch on, and it'll just take 5 minutes, all right? Now, for the sake of argument, say instead of calling this curve f, I called it f prime, because understanding the fundamental theorem goes a little better if you think about it as f prime. And why not? I mean, I can call that curve whatever I want. F prime, g, whatever you want. All right? So think of it as f prime, all right? if I'm finding area under f prime, then let's go here. I'm going to construct a foolproof argument. Wouldn't you agree that the derivative equals the derivative?
Yes.
We all agree that the derivative is equal to itself.
Yes.
Now, surely I used a little bit of a mixture of notations, but it's still true that the derivative is equal to itself. Now, if I move stuff around, the great thing of Leibniz notation is I can separate the differentials. And so if I moved the dx, then I would multiply dx over, I get something like that. Now, if I do that, then that's going to mean two things. First of all, I could say that now this area, isn't it f prime of x here and a small change here? So on one level, this represents area of a small rectangle, yeah? All right, cool. Now let's connect that rectangle to something more big. If I take dy, then isn't that a tiny change in y? And so it's also a tiny change in y. And we can get tiny change in y by saying what's the rate of change in versus y versus x times an amount of change in x. But it's a tiny change in y. So each area is a tiny change in y. And the total area is the total change in y. Now we know that we find total area by calling it a definite interval. We say total area under f prime now. I'm saying let's call it clear f prime. We've talked about how that total area of that summation can eventually be called this idea. Now the question, why do we anti-differentiate and plug stuff in? Why do we do that? Well, we just said that when you do those areas, you're finding total change in y. Well, total change in y, doesn't that mean the y values and how much they change? So the idea is that you're talking, think of that like if you find area under velocity, well then you're saying lots of little weight times times. And isn't that just lots of little movements giving you distance? And so the antiderivative of velocity and how it's positioned and how it's changed. So on one level, it feels like you're just making crap up. It's the antiderivative, go for it. But it makes sense. You're finding change in y in the original function. That says verbally then this means the area under a rate of change is amount of change. And that should be net amount of change. It can be increasing change, it could be decreasing change, it could be a little increase and a little decrease, and it's the net amount of change. So it's net change, not total change, which I'd have to use absolute value. All right, now that then is one way to look at the fundamental theorem. One way to write the fundamental theorem, which I cut off a little bit, is if you looked at the area under some curve f prime, then it's just the change in the original function. It's more common in textbooks that they just say, if you think of the curve as f, then it is the antiderivative, which we typically call big F. It's the same idea, the antiderivative of that. Right? This is the more common way to write the fundamental theorem. Okay? It just goes to what do you want to call the original curve, but it's still the same idea. All right? Now, that is all. From experience, last year I wrote a note, I just did all this in notes, and most people were just blowing right past it. They weren't even doing the notes because they were really good at this. They didn't see the point. So I felt like this time I'm just gonna have you go for it, and if it doesn't go well, then I'll help. The only one that might be iffy is the last one on the front page. I don't know if you've done population density. Have you done population density? So calculus tests so many things. It's so amazing, and you're just starting to learn. But I'm going to let you play with that a little, and rather than hand it to you, and maybe usually about a fourth of the people. All the way through it, and I'll help them. Yeah, the rest. All right, that is that. Tomorrow, you will have about a half-period quiz on derivatives and applications of derivatives. So that is the quiz tomorrow. It's derivatives, I think, were review 6. Look at that. And 7. And it might have also been 8, I think. I think those are all derivative and applications. So I would review those and make sure you're good. I gotta say, grading, they're pretty good. Make sure you know your first derivative, second derivative tests, your extrema, your inflection points, and all that good stuff. I must say, review 9, which I just gave you, the integration technique. Some of you are a little more rusty with integration technique, so we need to practice that a little more. Luckily, we're going to be doing integration applications for a few more days, so you will get practice there. All right. Questions on last night's homework? Did I put the key up to last night's homework? I did? Cool. Way to go, me. I feel like one of those questions missed the mark. The ones where the rate of change of this, I was trying to set the stage for today, and I fell apart. But that's okay. Questions on last night's homework? I have so many windows open. Oh, just shout them out. If you're raising your hand, I hope you're not raising your hand. Number 1. Okie doke. So last night's was review 10. And I could have sworn I had review 10 open at some point this week. Oh, man, I am just having a rough day. Freaking heck. Come on, baby. Okay, you said number 1. All right, I will paste that in. Doobie-doo. Okay, any others while I'm here so I can paste them in? 13. I would imagine there would be questions on 2B, but maybe not. I don't know. Maybe you're super brilliant. Some of you, I feel like you might not quite know when you don't know things. I don't know.
3.
Okay, 3. Okay, 3 I had a mistake on. On 4. 2. Now we're talking. Now we're rolling. $12B. 12B. Oh, 12B. Apparently I might have overestimated what you remembered. Okay, cool. Let's go. Alrighty. For number 1, are we talking the first one, the second one, or both of them? First one, okay. So cool. I don't know if you graphed it, but I'm just going to go straight to the area. Is the accumulation of many rectangles. So cool. All right. What did you say for delta x?
Oh, it's 10 over x.
10 over x. And what did you say for the x's at which you will find the heights?
10 over
Okay, perfect. Good stuff, good stuff. And then, what did you do?
We had, 10 over n, times 2 plus 10 over n I.
Okay, sounds good, cool. All right, now, there's not a binomial expansion component to that there, so fight the temptation to think you had to cube this whole thing. Isn't it just ready to be separated? Yeah? So the first separation is 10 over n times the sum of a bunch of 2's. And the next is, so you're good, 10 over n to the 4th times the sum of a bunch of I cubes. Cool. Okay, next. Sounds like you know what you're doing, so now I'm starting to worry that I made a mistake in my key. What's the sum of a bunch of 2's? 2n. Okay. And what formula did you use for the sum of cubes?
N times n plus 1 with all factors.
Okay. All right. So that sounds good. Now we're ready for the infinite limit. Ready? So for this, the n's drop out and I'm left with 20. Ready? Okay. For this one, I have a power match. It's n to the 4th and n to the 4th, so it's about the coefficients. So the first coefficient is 10 to the 4th, which is 10,000, and nothing else. Over 4.
So I had 2520, but you had 5020.
Yeah, I think I remember canceling something here. Why did I think there was 5,000?
But it wouldn't be over 2.
On my key, I had over 2. I think that's where I had it over 2. That's why.
That's what I thought it was supposed to be.
So I'm a bit of a knucklehead. There's two ways to write this formula. One is to say all of it over 2 squared, and the other is to say just the top square root of 4. And I did take it, keep it easy, keep it down, please. I screwed up remembering this, and so you're absolutely right. It sounds like you know exactly what you're doing. It is 2,520. So it sounds like I had a mistake on my key number 1A. Should have been 2520. Thank you. Okay. How about B? Should we talk about B? Sounds like you know what you're doing in this meeting. Okay. All right. I thought I heard somebody ask about 13. You still need that, somebody.
Yeah.
Okay. Okay. So what's the first step is what it's all about. What's the first step I do here, people? Divide. Okay. X squared plus 1 is nonlinear, so I have to use more of a long division approach. Don't forget your placeholders. Okay, so if I take x squared into x cubed, how many times does x squared go into x cubed? Think this way. 1x times, yeah? Okay, if I multiply, record it here, and then subtract, then my next line is nothing, nothing, x plus 4. What do I do with that? Yes. Okay. Now that's a step forward, but I'm definitely not out of the woods. This is still a bit of a mess. Okay, I think the x is obviously fine. How do I deal with that second term? Yeah, you got to separate it into x over x squared plus 1 and 4 over x squared plus 1. All right. And I really should be writing this. I had one professor who's just terribly crazy. If you use sub when it was all together, he would definitely have a problem. So I'm going to write those all separately. All right. So what's the first antiderivative? Okay, cool. So this one, bit of a mess. What do you do?
Um,
This one's where you think, use sub. Think, use sub. So if I do use sub here, what do I let u equal?
um,
Correct. And therefore du is 2x dx. Given that I only have x dx, I'm going to move that 2 over and call it 1/2 du equals x dx. So that when I go to substitute in, the x dx becomes du over 2 or 1/2 du, and the denominator is just u. Cool? That's 1/2 log of the absolute value of u, and if I then sub back x squared plus 1. Just for the sake of practice, what if in the multiple choice you didn't see that? What's another form of that you might see?
natural log of x squared plus 1 x squared.
Square rooted, because if you move that half up, it could be a fractional exponent. Okay? So, I'm cool here, 1/2 x squared plus that I've got taken care of. What about that one? Non-natural log. That's actually a kind of a trick question. It's a memorized derivative. That's the derivative of arctangent, which occurs to me after somebody told me that we didn't do arctangent or we didn't do a lot of arctangent. Did you not? We did it, but it's at the end of it was right when it said 65 or something. So maybe it's just not all the way in yet. But this, the derivative of arctangent is that. Now we will actually talk a little bit more about why that is tomorrow. We're going to develop that, but for now, just roll with it. This is 4 times arctangent of x plus. That was a doozy. Cool? Okay. While you asked about this, I had about 5 people per class make the same mistake here. If I have a sum in the numerator, can I split it? Yes. If I have a sum in the denominator, can I split it? 100% no, 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 no. You just broke mathematics, my friend. You cannot do, think about it. Is this equal to this? Yes. 1 equals 1, that's true. Can I split a sum in the numerator? Yes. What about this? Is this equal to that?
No.
No, 1 is not equal to 4. You cannot split a sum in the numerator. You cannot in the denominator. You can't do that. Okay. Okay, is 3 still a question? This one I definitely had a question problem in the key here. So, first of all, which did you choose? Now, I said in number 4 you should have chosen A. I bet I tricked you there. Because it's not A, it is. Oh, you should not have chosen A for. Oh, shoot. Oh, good. Not have chosen it. So I was right. No, I was wrong. No, I'm right. All right. So, which one is it? Okay. So first of all, what's the delta x? The delta x is 3 over n. So this is out, and this is out. All right. Because they had the wrong delta. Okay. Furthermore, we know that when you start somewhere like 2, isn't it 2 plus some number of that same delta? So shouldn't it be 2 plus some number of, again, 3 over n? And this has just 2 plus some number of 1 over n. This has some number of 3 over n's. This has the right number of deltas. They're just using i's instead of a's instead of i's. So it is. Good. You want to match the delta, and that scratches A and D, and then you want to say, all right, I know that the inside is f at the starting point plus some number of delta x's. And in this case, I know that to be 3 over n's. Okay. And then do we need to go over 4? Okay. Anybody need 2? Yes. 2 is, yes. So let's talk about, let me do I imagine the left hand is the hardest part. So let me get really quick to that. Crank out the right hand because we can use it. Okay, so first of all, I hope you found delta x to be 6 over n. And then I hope you found the f-ats to be the starting point, -1, plus some number of 6 over n's across. So if I then use the function, then it's blank squared plus 2 blank. And in those blanks, I have to put this mess. Okay, now the next issue is, can you get that expanded without error, which is no small task. Check your binomial expansion. When I square this, I get a positive 1. When I multiply that by 6 over ni, and again add it to itself, it's -12. Or -2 6 over ni's.
Are you doing right hand or left hand?
I'm doing right. Okay, but then I'll do that.
-1 plus dot 1 is -1.
Why isn't it -1? Because you're starting at -1. Whether you do left hand or right hand, you're still starting there. The only question is, if it's right hand, then it's starting at -1 and going over 6 over n. But if it's left hand, then the first x is -1 plus no 6 over n. You with me? But either way, left or right, you're starting at the left edge -1. Okay? Does that make sense? Okay. So now I'm expanding this baby up, and I get +1 minus 2 6 over n i's plus 6 over n squared I squared minus 2 plus 2 6 over n i's. Do you agree with that? Yes?
Yeah.
Okay, now let's talk cleanup. The 1 and the -2 are constants, and that goes up to -1. Blessedly, the normal i's, I have a -2 6 over n i's and a +2 6 over n i's, so they drop away, which is the way. And then I have a 6 over n squared I squared. Cool? Okay, now then, if I blow this up, I have 6 over n times a bunch of -1's and 6 over n cubed times a bunch of I squareds. You tracking? Okay. Now, when I use the formulas, what's the sum of a bunch of -1's? -1 n times, and the sum of squares is n times n plus 1 times 2n plus 1 over 6. Are we done? Okay. Then, are you good with the infinite limit? Are you getting pretty good at those things? For example, what is this approach? -6. And this, as I get negative cubed to negative n cubed and n cubed, what does this guy go to? 6 cubed times 2 over 6, and so that feels like -6 plus When I drop a 6 and multiply by 2, I get 72. So 66 is my answer. Cool. Now let's compare that to the left hand, which is probably the biggest question. The good news is that a lot of that work will be exactly the same. The first difference is that if it's left hand, instead of starting at 1 delta over, I'm starting at no deltas over. And the right side, instead of getting all the way to the last, I'm getting to the minus 1, the one right before that. So that's the first change. Are you down on that? Okay, change 1. Now, all this work is exactly the same. So I'm going to jump down to where it starts to be different here. When I say 6 over n times the sum from n minus 0 to n minus 1 of negative 1, and this is 6 over n cubed times the sum of I squareds. When I go to use the formulas, things will change. Should I give you a minute to catch up, or should I continue? You're good? Yeah, it's all that work is exactly the same. You definitely don't need to redo it. Okay, now then, this here formula is if I add negative 1 to itself n times. So think about how this will come out. Wouldn't this, when I equals 1, I get a negative 1. And when I equals 2, I get a negative 1. And when I equals 3, I get a negative 1. And I keep doing that till I equals n. And I get a negative 1. Now in this case, the counter says, when I equals 0, I put in a negative 1. And when I equals 1, I put in a negative 1. And I'm going to go through, when I equals n minus 1, I'm going to get a negative 1. Question then is the number of negative 1s I have here the same or different? Well, it's the same. I mean, I'm starting here a little different, but I'm ending at an earlier point. So this sum of negative 1s is exactly the same. It's exactly the same. It's still negative 1 n times, because there are still n rectangles. Period. Okay? Now, the next part, a little less obvious here. This formula is predicated on it starting at 1 and ending at n. This one doesn't start at 1 and end at n. It starts at 0 squared and ends at n minus 1. Okay? So surely then this one's going to come out a little bit different. There's two schools of thought here. I want to figure out, so what does this come out to formulaically? What's one way to come up with that? One way is to take what this was and say, how did it change? Well, what was this? It was this, but now we're losing a, from here to here, what are we losing? And that n squared. We're not getting that n squared. Do you see what I'm saying? No? Yes? Okay. So one way is to say, I'm going to take that big gobby formula and subtract away an n squared. And that's fine. The other way to do it that I prefer is if this is the formula you use when you end at n, then couldn't I use that same formula, but here instead end at n minus 1? And so in place of each of these n's, put in a n minus 1. because I'm not ending at n anymore, I'm ending at n minus 1, then I only need to put in an n minus 1 there, and an n minus 1 there, and an n minus 1 there, which is pretty gross. And adapt the formula a little to my new finish point. The good news is, though, that the limit comes out exactly the same. What does this approach? Still -6. And despite this being totally wacky different, do you agree it's still n cubed in the denominator and n cubed in the numerator? And do you agree that it's still 6 cubed times a 2? And there's a big mess house going on, but as far as lead coefficients, it's still a 2 and a 6, so it's the same. Now, does that make sense that left and right hand are the same? For finite rectangles, should they be the same? Surely not. But for infinite rectangles, should I get perfect either way? And the answer, yeah, they did the same. Now, the question then is, why not do right every time? And surely you'd want to do right every time. Right is a heck of a lot easier than all this moment. I just wanted you to see it once, but in the future, I'm only going to make you do right, okay? And then number 12, B. I think somebody asked about 12B, yay?
Yeah.
Okay, so now that I have told you that the derivative of our tangent is 1 over 1 plus x squared, now I'd like you to think ultraviolet voodoo. U dv equals u d minus v du. So what should you make u? Well, the best is log, no log. The next best is inverse trig. Do you have inverse trig? Yes. So let u equal arctangent, and therefore dv is just that little dx there. Du is the derivative of arctangent, 1 over 1 plus x squared, and v is straight up x. So that uv is x arctangent of x. That's all good because we don't have to integrate it. But v du, shoot, is now a u sub problem. And you can use u sub with log there. Okay, make sure I get this by the end of the day. How about 20 days?